Now let's talk about the relationship between electrical field and electrical potential, basically E and V. That is called equipotential lines. So what are equipotentials? Equipotential lines are a visualization tool. They illustrate where the potential is a constant. Equipotential lines are actually projections on a two-dimensional page of a three-dimensional equipotential surface. So think of this as a contour map. Contour maps are also the same way drawn on a 2D surface for a map that shows ridges and depths and flat surfaces, right? So where there are more lines, you know that has a higher elevation. So equipotentials are contour maps of the electric field. So these are examples of some basic type of electrical fields that are generated by certain types of charges. So all of the arrows shown in black are the field lines around the charge, and the equipotential surfaces are the dotted lines around them. So if you have a point charge plus, the field lines go outwards, and the electrical potentials are going to go around them. If you have an infinite sheet of positive charge, what you are going to observe is that the field lines are going to be spread out evenly all the way up till infinity along the electrical field. For an electrical dipole, which consists of a plus and a minus charge, electrical field lines will be given as these. So things to remember about equipotential lines. Electrical field must be perpendicular to the equipotential lines, otherwise work would be required to move a charge along the surface and it would no longer be equipotential. In the static case where charges are not moving, the surface of a conductor is an equipotential surface. Otherwise charges would flow and it would no longer be a static case. Some important things also to remember about equipotential surfaces. The lines are going to be spaced closer at the end with more curvature, right? Which basically means higher electric field will lead to field lines being closer. Near the surface, equipotential lines will have the shape similar to that of the object causing the electrical field. However, further out, at really large R's, those electrical fields will almost look like they are spherical or circular in nature. Now let's do an example. You wish to charge a Van de Graaff generator to a potential of 240 kilowatts on a day with average humidity and electric field of 8 times 10 to the 5 newtons per coulomb, or greater ionizes the molecules, allowing the charge to leak off the Van de Graaff. Find the minimum radius of the conducting sphere under these conditions. So this is a great example. This actually allows me to talk about the relationship between E, electrical field, and V, potential. So E, we know, is given as KQ over R squared. And we know V is given by KQ over R. Okay? So how do I find the relationship between these two? I see that this is exactly the same as that. So I can figure out KQ is VR from here, right? Sorry, VR from here, and I can plug that into here. So this will give me E equals VR over R squared, or E equals V over R. If I replace that R with a D, it becomes my famous ED equation. So the relationship between V and E is given by V equals E times D. So that's something that we should all know. So this is the relationship between E and D. In this particular question, it is asking me, what is the minimum radius required for the Van de Graaff when V max is 240 kilowatts and E max is 8 times 10 to the 5 newtons per coulomb. Okay? I know this relationship. Okay? I'm going to get rid of this one for now. We'll talk about this later. But this is what I want. So R can also be given by V over E from here. Yes? So that means this is easy now. This is going to be 240 times 10 to the 3 watts divided by 8 times 10 to the 5 newtons per coulomb. I just solve for it, and I get that my radius has to be greater than 0.3 meters, or about 30 centimeters.